Hey guys, welcome to another Science 10 chemistry lesson. Today we're going to talk about molecular compounds, and again, this is carrying on from previous videos where we've talked about naming ionic compounds, talked about naming polyatomic compounds. Now we're going to get into more of the specific rules that relate to molecular compounds. Now, a molecule forms when two or more non-metallic atoms bond together. And again, a key point there, ionic compounds, I mean, we have a metal and a non-metal, so a cation and an anion, whereas in a molecular compound, we have two non-metals. And it can be made up of atoms of different elements or of atoms of all the same elements. So example, you can have CH3OH, which is methanol, or you can just simply have O2, which is oxygen gas, the gas we breathe in. And something that, and key to note, I mean, we don't actually just breathe in oxygen by itself, we breathe in O2 or two oxygen molecules together. Now recall that the formula unit of an ionic compound represents a ratio of ions in a crystal lattice, and that was from a previous lesson where I showed you pictures of the crystal lattice and how it actually lined up with the specific ratios of molecules within that compound. Now in a solid ionic compound, this lattice extends in all directions, so it can go kind of build out any way it wants, really kind of like a snowflake from the center. Now, a formula unit is not just an independent unit, it's just one part of a crystal lattice. And molecules are independent units made up of fixed numbers of atoms bonded together. So with ionic compounds, meaning if we're talking about NaCl or table salt, you can have a giant piece of table salt or a small piece of table salt, but it's always a 1-to-1 ratio where you have one sodium to one chlorine, and they just keep building off each other. With molecular compounds, what this is saying, being independent units, you can't have a big piece of this molecular compound, a small piece of this. They have a fixed number of atoms, so it's always a specific number that you find for that molecular compound. So unlike ionic compounds, molecular substances, though, can be solid, liquid, or gas at room temperature. They tend to be poor conductors of electricity, whereas we were having ionic being good conductors, and they do not dissolve as well in water compared to ionic compounds. So some examples of common molecular compounds, and these are things that you should try to start to remember because you're going to see them coming up, and if you always have to go back to your book or you're writing a quiz or a test, it's going to get really hard when you're getting a whole lot of these compounds. You're like, what was that one? What was that one? But anyways, we have C12H22O11, which is sucrose, CH3CH2OH, ethanol, CH3CO CH3 is acetone, and CH4 methane. And there's a real big one, methane, very simple, CH4. I can promise you that will come up at a later date. Now the atoms in a molecule are joined together by covalent bonds that form when atoms share electrons. Now this is a lot different than ionic compounds, whereas each pair of shared electrons forms one covalent bond. So electrons are not transferred from one atom to another as they are in ionic bonds, where we are talking about in uh, sodium chloride before, or table salt, where we had that one electron leaving the sodium and going to the chlorine because it needed an extra one so they could each have 8 in their valence energy shells. In molecular compounds, we have these covalent bonds where they're sharing. Now, chlorine gas is an example of a substance that has molecules formed by only one element. Now, each chlorine molecule is made up of two chlorine atoms joined together by a covalent bond. And so the chlorine atom has seven valence electrons in its outer energy level, and we talked about that. So an additional electron is needed. So it wants to have 8 to be in the most stable format. So a molecule of chlorine gas is created when two atoms of chlorine each share an electron to form a covalent bond. So if we look at this picture here, if you can follow along with my mouse, you can see that from this molecule or atom of chlorine and this atom of chlorine, they each share an electron with each other. So now we have 2, 4, 6, 8 in this shell, and then we have 2, 4, 6, 8 in this shell. And so they both have 8 now in their outermost shell, and they're in the most stable form they can be. So other examples of covalent compounds that you would see would be H2O or water, NH3 ammonia, and C12H22O11 sugar. And so you're going to see this sort of sharing going on so they can be in their most stable format. And it doesn't always have to be they just share one. Sometimes they could share all the way up to 7 and 8 if they need to. Now, in some covalent bonds, the atoms share more than 2, just like I said. So example, nitrogen gas, N2, and you can see here, it is sharing 6 electrons in its outermost shell. So an atom of nitrogen has 5 valence electrons. So I mean, it needs 3 more. So if they share 6 between them, plus with the 2 extra on the outside here, they're going to have 8 in their outermost shells. And again, that puts them in their most stable form. Now, there's certain molecular elements that are made up of only one type of atom, and this is a table here that you're gonna need to remember, because it's when you're writing out formulas, when you're building compounds, when you're doing tests and quizzes, these molecular elements that are made up of only one type of atom are always in this format when they're by themselves. So what we call monatomic, meaning they are only by themselves, they're not with another element the same as them. You have carbon, all the noble gases, and all elements. So they are stable by themselves. But being diatomic, however, you have hydrogen. So if we look here, we have hydrogen gas, nitrogen gas, oxygen gas, fluorine gas, chlorine gas, bromine gas, and iodine gas. Now, they're all in gas forms. And polyatomic, we have ozone, which is O3, phosphorus, P4, and sulfur, which is 8. So when we start writing out compounds, and if you have an S by itself, for example, you automatically know to put a little 8 subscript beside it, because that's the most stable format, and that's how you're going to find it. Now, dealing with molecular compounds that do not contain hydrogen, so a binary compound is with 2 elements. So rules for naming binary compounds not containing hydrogen are similar to the rules for naming ionic compounds. So again, for molecules though, we have Greek prefixes which are used to indicate how many atoms of each element are present in the compound. And it always starts by naming the first compound first, or first element first, just like we did with ionic compounds, and then the second. So if we look at the example of P4O10, this is called tetraphosphorus decaoxide. And I'll show you a table here in the next slide where the 4 means tetra and the deca means 10. And we know that P is phosphorus and O is oxygen, but because it is the second element, we change the ending to "ide", so therefore it becomes tetraphosphorus decaoxide. And so here are all the prefixes all the way up to 10 that you will need to remember also. 1 being mono, 2 di, 3 tri, 4 tetra, 5 penta, 6 hexa, 7 hepta, 8 octa, 9 nona, and 10 deca. Now, any compound that does not have a metal or an ammonium ion in its formula is molecular. So again, no metal and no ammonia ion means you got a molecular compound. And the format for naming binary molecular compounds, so binary meaning 2 together, not containing hydrogen, is you have the prefix first, so from that previous table, so if we just go back, so from this table here, so the prefix, followed by the name of the element, followed by the second ion, where you use the prefix, and then you change the second element's ending to "ide", just like we've always been doing. So note, here's a couple, one exception to the rule, that the prefix mono is not used when the first element is only one atom. So when the prefix mono is required before oxide, for example, 2, the last O in the prefix is usually dropped. So it is monoxide, not monooxide. And if we look here at these 2 examples, we have N2O and PBr3. We have dinitrogen monoxide. And PBr3, again, if we look up at this rule here, note that the prefix mono is not used when the first element is only one atom. We only have one atom here of phosphorus, so we don't say monophosphorus, we just say phosphorus. And then we have bromine, we change the ending to "ide", and we have a 3, which means tri, so it's phosphorus tribromide. Now, what I want you to do here on this slide is I want you to practice naming these. So if we just get our little pen out here and we try, so we have CO, and again, we don't use the beginning letter or beginning prefix mono. So we just have carbon. I can't write very well with my mouse, but carbon. And we have one oxygen, so it becomes monoxide. All right. Now, let's just see if I can make this a little better. We try the next one. We have SO2. Again, we know S is sulfur, O is oxygen, so we have sulfur monoxide. CS2, we have carbon and sulfur, so then we have carbon disulfide. I just noticed I made a mistake here. If we look back at this one, I have SO2, not SO or SO as what this actually means, because I wrote monoxide. So if we just get rid of the mono part and scratch that out, because we have a 2 here, it is dioxide. So we have sulfur dioxide. Now if we look at the actual full names and we go to name it, we have dinitrogen, so that means we have 2 N's, and we have trioxide. That means we have 3 oxygens, so we have N2O3. We look at the next one, we have carbon, so we know we only have 1 carbon. We have tetra, which is 4, so that means we have CCl4. And the last one, tetra phosphorus, so that means we have 4 phosphorus. Deca, which means 10, and we have oxide, which is oxygen, so it's O10. So again, those are the rules for naming molecular compounds. A few little differences from the ionic compounds and when we're dealing with polyatomic, but now you have all the rules of naming ionic compounds, polyatomic ions, and molecular compounds. So hope you can take something from those lessons, and we will see you the next video that we have.